speak about something very interesting. You're welcome to join us for dinner at usual place, Evelyn's restaurant at Eastern Avenue at 6:45. But please let me know right after the talk whether you can join us.
Okay, he's going to do the slides. Okay, thank you. Okay, so I'm going to talk about, this is a work in progress. I've been working on this for about a year and a half in between the writing up the notes of Henry Gould, which light lowers and raises the front light.
Oh, the black switch kills the front light.
Okay, and then we'll keep it on until we get there. All right, so our object of study, we're going to be 10 little kids, and we're going to work with squares. We're going to make n by n rectangles or squares, and we'll pretend we have a bucket of paint, more than unfortunately available here. We have lots of colors, and we want to color these squares with paint, and in the end run we want to try to make an approximation of how many of the edge adjacent squares share the same color. So that's the expected value. So to begin, we need to be able to enumerate the number over here. We want to enumerate I'm going to start pretty simple. I'm going to let this be n. If you're really subtle, you'll notice at some point in my program I interchanged the roles of m and n. It doesn't in the long run matter, but for our purposes. Okay, we want to enumerate these, and we have C colors. Okay, so you can kind of guess how many of such, if you had C colors, how many ways you could make this. What would they be?
C to the power mn.
Yeah, C to the power mn. Now we're going to enumerate this because I want to get some S information. And so S is the number of edge adjacent pairs, and D is the number, or I'll have S and D. D is the number of pairs that don't have the edge adjacent pairs that don't have the same color. Well, S does have the same color. We will enumerate this. We'll fix M as numeric, and we'll use the transfer matrix method. And one of the favorites of our founder here. Form generating functions, to form a collection of generating functions and these functions will be rational in T and C, such that t to the coefficient of t to the n is the number we want. Such that coefficient of t to the n is, in fact, c to the mn, the number of edge adjacent, number of n by n grids which can form a C colors. And now we know what you can guess. It's a nice, Mabel likes this because this is a very simple generating function. It's basically a geometric series. But we're going to begin because we want to, when doing a transfer matrix method, we need
What are we counting?
We're counting, you're fixing M, we're going to count the number of n by n grids where you would count C colors to make them.
Yeah.
And so then
So let's see the power n.
That's right.
There's some conditions.
We will then, yes, yeah. I'm going to start very basic, and then I'm going to leave quickly.
Oh, right now we're deriving this.
Yeah, and then I'm going to adjust what I did to get the S information. You're right, if this was the question, I wouldn't even do it this way. Yes, we know the answer. This is the answer. I completely agree. And it's a nice, simple geometric function. You wouldn't waste your time. Yes.
That's nice, and you proof.
Yes, a new proof. So a new proof. Using Eckhart could do this. We didn't have anything better to do.
It's a computer proof.
That's right, it's a computer proof of this, yes, yes. So Eckhart would be approve of this proof. This is Eckhart approved proof. He would be for the slightly happy computer. So, yeah, it's easier for, I think, if I explain this with an example. And I'm going to, for our example, I need to, because when doing the transfer matrix method, I need to have states. And the nice thing about the states is you only have to look at the very last row of your grid, and it's the number of set partitions of that row. And what is the number of set partitions?
The numbers.
Bell numbers, yes. Let's do it. So, yes, bell numbers, yes. So the nice thing is the states for a fixed m is b to the m, the bell number. And the computer can quickly build this. We dim the lights. It uses the program states. Just to convince yourself. So we're going to do our example with 2 states, because we can only draw so much in a short period of time. But lo and behold, I should have the program in here. So states, 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 states. And so here's our program that tells us the number of states in the k by n. And if you plug in states 3, here we have, you see the bell numbers. This is all one color. Here we have first 2 share one color, and the second one is a different. And here's states 2, and if you had very great fun, you could type in states 1, states 2, states 3, states 4, and you'll see it's the bell numbers. Okay. Now, when building the transfer matrix method, we have to talk how one state goes to another state. So we're going to work to help us explain this process, how the computer does this. We're going to work with, we're going to fix n is equal to 2. Okay. And we're going to have 2 states. So 2 states are 1, 1, and 1, 2. In the following diagrams, the computer has to figure this out. How you would pass state 1 to state 2. Now I want to do this with an arbitrary C coloration. So here are the patterns. You start with 1, 2, and then you could put in 1, 2, 2, 1. Now 1, 2 here, put a 1 here. I don't want to put a 2 or a 1 here, so how many colors could I fill that with? If I have C colors, it must be C minus 2. Yes, I'm proving wrong. We'll pretend we have enough paint, so you throw another color in there. Then again, we have another C minus 2, C minus 2. Here we have another C minus 2. Now this I don't want to use 1 or 2, so I put a C minus 2. And in this spot, I don't want to use 1, 2, or this, so I have a C minus 3. And then you add them all together, and you get the states you have, and that is done by the program. If you're really clever and you saw all the way up there, it's done by the program. The machine does it for us automatically. State 1 followed by state 2. You put in your states, and you have to put in the dummy variable C. So this is state 1, and then you can see how many ways state 2 could follow it. And that's in our machine. There's a clever way to do this with, I'm not going to explain all.
So you're counting with restrictions.
Pardon?
You're counting with the...
No, not this one yet.
I understand, so...
Go ahead, okay.
So I understand.
Okay, let me understand.
You're just improving the trivial result?
Yes, improving the trivial result. I'm going to put the S's in it, yes.
So I'm done.
That's all right, no.
I don't understand what do you mean by C minus 2, C minus 3?
I'm assuming I have C colors. I have a bucket of C colors.
Yeah.
And I know in this last row I have state 1 and just how I have, let's say I have a color red, white here. Okay, well we'll just pretend we only have 4 colors.
Oh, so 2 different colors.
Yeah, 2 different colors. I have a green. And now I want to fill this.
The premium case even for a fixed m equals 2, that's what you're doing, right?
Yes. Yeah, I'm just doing 2 states to demonstrate what the machine does. It would have to then determine the options that could be filled in with
it's state 1, 2, so
yeah.
You have 2 different colors.
Yes.
And then you look what can come next.
That's right. Okay.
So from 2, 1 to 1, 2.
Yes, and this is still considered state.
Yeah.
State 1, 2. Remember, we have a canonical form. We do this. This is the same as saying
state.
I mean, the way you could do this is in our final row. When we do when we have to look at when the m is fixed, m is 2, or m is 1. We have a.
So this is m is 2.
Yeah, m is 2, and so we have 2 possible states. They could share the same color.
Yeah.
Or they could have 2 different colors. In other words, you have the partition row space 1, 2 all together, or you have the partition 1 and the partition 2.
Oh yeah, and then it starts talking.
Yes, and so that's why it works. So it basically, you take your final row and you set partition it. And for each piece of the set partition, you give it a color, different color.
Okay.
Yeah.
Thank you.
Yeah. So either you have one whole thing or you have two separate pieces. Yeah. That's what this is doing for you when you make the states. That's why it's the Bell number. Now, yes, we'll get to the S. I promise we'll move quickly. We'll get to the S pretty quickly. I agree this isn't too exciting. The machine does all this for you. It is this fancy way you can tell it how to do this. And so it would automatically do this for us in the program, as I said, state 1 followed by state 2 followed by C. So if we go back to our program, and we don't need to worry about, it's all hidden in here. I promise you, if you really want to read the code, I'll be certainly glad to let you read it. Be careful to write. Here we are, state 1 followed by state 2, it does it for you, and lo and behold, if you add all those up, this is the number of ways. You could have C squared minus C ways of doing it. So now if state 2 follows state 1, I'm sorry, if 1, 2 follows 1, 1, the next case, now this is 1, 2 following 1, 1, we also get C squared minus C. If you start with state 1, 2, and then you want to go to 1, 1, we have C. We'll show all these on the board. The machine does this in nanoseconds. And then if you had state 1, 1 followed by state 1, 1, we also get C. So these are nice simple things, but it can do this for, the machine has no problem doing this for huge size now. So for this one, we'd have, notice I have 1, 1. You can either fill it with 1, or I can't use 1 here, therefore I must have an option of C minus 1, and if you add these together, you get exactly what Eckhart said you got, or, well, Eckhart Jr., I guess I should call it. Mine's not Eckhart, sorry. You get C. And we can do this for the other states, and we'll come back. We need to keep these because we want to come back when we do the D information. Unless I fill this one in. So here we have, this is 1, 2 followed by, I'm sorry, this is 1, 2, and then you follow 1, 1. And then this is 1, 1, and you follow by 1, 2. So this one you'd have to put as C minus 1. And then you add them all together. The number of ways, you go C2, C minus 1, plus C minus 1, C minus 2. Lo and behold, when you do this, you're going to get C squared minus C. Okay, so the machine does this states, and then we have to build a system using this. This is going to be the basis for our system of generating functions we want to build and solve. And when doing the transfer matrix method, the number of variables we have is actually related to the number of states. And so for example, this basically you have each variable and to some state, and this means your grid ends in that state. So in this case, when m is 2, we're going to have 2 variables. And this is saying how many ways can we count that we end in 1, 1? Well, you have to say how could 1, 2 pass to 1, 1? And then you have to see how could 1, 1 pass to 1, 1? And this first one is just the case where you have only one row. T, the exponent of T, I should mention, counts the number of rows in our grid. And there's C ways to do this. So now if you put this all together, we get one. Here's our first function we have to solve. The machine has to perform. Oops, wrong paper. Let's pull ahead myself. You end up shifting, you end up putting n to m plus 1, you end up pulling an extra t out, and then we will fill this in. This thing we know 1, 2 to 1, 1 has a state of C. It's this is starting with variable 1, 2. And this one you have up here, you started with a 1, 1. You do a similar thing for the other state. And if you do that, you want to end, see how many ways you can end with 1, 2. So if you do that, remember we were looking previously, this is 1, 1, so this has to associate with the variable x11, and we're going to tackle one to make sure we end up with a 1, 2. So you look at the state that you had from our TS1 thing. The extra T means because I actually have to have 2 rows, and when I shift the variable to get the appropriate generating function, we end up having an extra T. And this one we started with, and then 1, 2, we have to add another row and end up getting 1, 2. So the machine forms for each state, you're going to form an equation. You then solve, the machine will automatically solve this system of BM equations, Bell number equations, and then adds up all the solutions and puts it in a beautiful, nice form. And this is done by the program. We didn't have any sense to know what this is. K, C, T. But my K in this case corresponds to M. This is numeric. This is symbolic, and then this is my variable, so that's a t to the nth coefficient, is the coefficient is going to be c to the mn. So, lo and behold, the machine whips this up for us in no time flat. Like I said, it really does like generating functions.
Not for K with 100, then it takes a while.
Yeah, it probably does. It didn't take any time for 4 or 5. I mean, it went up to 10 very nicely, yes. And then it's like, oh yeah, we're just like, lo and behold, yes. And then you'd say, why bother to do this? I mean, yes, it's nice, the machine does it for us, and here's the output. I think I could go a little faster through this. Must have lost my... Yeah, and here's the output. So here is when M is 2, and lo and behold, you expand, and you get your nice M is 3, M is 4, M is 5, and you get to see that you get your nice powers you want. Okay, now what's the point of doing this? You'd say, well, I'd like to talk about getting additional information, and it's much easier to get this additional information with this set up. I mean, otherwise, I wouldn't waste my time doing it. It's a nice programming exercise you might give your undergraduates to see if they can figure this out. But, all right, now I have to define. Remember, we said I'm going to keep all this in here. So I'm going to just adjust it. We're going to do what I used to hate when my professors did. We're going to write over. Okay, so we're going to let S be the number of edge adjacent pairs. With the same color. And D be the number of edge adjacent pairs. And I'd like to incorporate this information into how one state can follow the other. The states don't change, but we have to incorporate a little bit differently our information. So let's go back to here, and I'll keep this as round 1, 2. Now if we look at this, for each one of these, it's no longer enough to just get a numeric number or something like before you would have a 1, 1. Here we'd have a C minus 2, C minus 2, a C minus 2, a C minus 2. It's no longer enough to get that. We want to incorporate our S and our D information. So if we look at this, we have to look how we go down.
So you have to tell what S and D.
Yeah, I did
Yeah,
it.
you already did?
Yeah, it's over here. These are the number. S
Oh, yeah, yeah, yeah.
Yeah, see, I said the board gets a little screwed up. Okay. Right. So we have to look at this, and you're going to say, you're going to do it vertically. What you're going to do is, how many ways could this change? Well, this is the same, and this is the same. So this is going to be an S squared. You're going to be looking vertically, how many of these would be the same color. This one, different, so this is a D squared. This one's different. You're going to look vertically to tell you how the S and the D change. So you got to look how they're changing. Up to this point, you know all your S and D information. The only difference is you're going to have to adjust it by what happens when you add on the final row. Okay? So this one we have to add, we get different. This is a D squared. How about this one? This would be a
SD.
SD, yep. This is a D squared, this is an SD, and this is going to be a D squared. And you do this for all these pictures. Okay? And the machine spits out how to do this. And this is done with the program. If I had enough time, I'd draw them all in. I'll just assume it's
So you only look at vertical differences?
Yes.
Not horizontal?
Well, I build it in when I do the system, when I solve for it. Yeah, so I'm looking at
now,
this.
yeah.
Yeah, but right now I'm only looking at how it changes.
Yeah.
So this is priori, you know, this is all known in terms of the
Oh, yeah, this would be part of the
SDs,
state.
yes.
Yeah,
And
yeah,
then when you go to the
horizontal
state, you have to see how it changes. Yeah.
Horizontal one could be think of later
Yeah.
for the state.
Yeah, and when I build the equations, it changes a little bit too. Okay, so now it's built in there. So that's all done. What did I call this program? You think I remember too many? And this is all done with, well, this is a really fancy name. We took our state program, and all we did was we tucked over the fact that we used a D at the end. So this is all done for us. And I'll look at the results of that, and then I'll show you how to adjust the generating functions. Now, okay, so we now move yes. And we do have to, when we do the generating functions, we do have to be very careful about building in where the horizontal S and D's are. So here we go, and this is what happens. And if you would put S and D equals to 1, you get back to the original states for C. I'll let you, if you want to write these down quickly, go do it, but I mean, they actually do check out. I did. And then you have to set up, you have to adjust your program that sets up the generating functions, is one for each state, and then solves for it, and this is done with this program. And you were concerned about the horizontal. It's the horizontal adjacencies put in here. You have to worry about. Do you pick it up there when we're doing the S and D when you form the system? Okay. So when we set up the system, we get this, and the only difference in our system setup is we're going to change all these. For example, if we're doing the S and D system setup for this case, when M is 2, well, this one has a pair across. Now this one, you'd have to put in what you got here. You put in this, and we're going to end with 1, 2. And since this is S across, you're going to put an S here. You're going to end up having an S each time through because this one ends up with an extra S. You do pick it up here when you do the system. You asked me about the horizontal adjacency. You pick it up when you form the system. And then this thing ends up being, you're not going to be C, it's going to end up being times this. And we can adjust all of these. It's okay, so we can adjust all of these as follows. Then you solve it. Now let's look at some of these solving. Solving gets a little more, this we don't want to do by hand. We really wouldn't want to do this. This is quite tedious. And unfortunately for symbolic things, the machine has to have, when I'm solving this, I'm going to get a rational function in S, D, C, and T. Now, to be really efficient, I can do this for a symbolic C when m is 2 and when m is 3. It gets really bogged down, at least for the machine I have, when m is 4. So you have to put in numeric numbers for it. But here is, in fact, for example, that's not the one I wanted to show you. You get this. So here it is. If you want to look at the number of 2 by m grids with C colors, and you want to have the S as the number of edge adjacent pairs having the same color, D is the number of different, and you want to look at the coefficient of t to the n, and that tells you the information you want to know in terms of S and D.
So when S is 0 and D is 1, they're all different.
Yeah. Mm-hmm.
So can you get interesting sequences in Snow if you?
I haven't looked at it. You probably can,
Yeah,
depending on what you put in S and D.
Yeah,
Now, I already if you did the check, if S and D precisely are 1, you get back to what you want. And this is, in fact, the way this particular thing is. You would add these two together. This is, in fact, correct for if you just have one row, the number of ways you could do it. Because if you remember, if you have one row, just to convince you for a very simple case, well, how could you do this? I'll erase this off now.
Well, you should expand every coefficient.
Yeah, and then we could do that, and you could collect in terms of power
Yeah.
fractions. Yeah, I just took that out. That's
Yeah,
in
right.
another program. Just took that out for the time being.
Yeah.
But yes, you can. Yes, we can do that, and then you could look at it slow. And yeah, you're correct. You could split each one up into a power frac.
No, very interesting to experiment.
Yeah.
And to
Oh, yes.
compare it.
Yeah, but for just to convince you that if this is 1, 1, this would be the C ways you can do this. There's 1S, is T, and if you have 1, 2, there's C times C minus 1 times D. And if you add, this way, add that up, that's precisely what this coefficient is. So it does give it to you. All right. So now we're ready to try to calculate the expected value of S, the number of what we expect if we give you a random coloring. How many of these edge adjacent pairs would be the same color. And so to do this, we're going to have to make a probability generating function. All right. So what we're going to do is we're going to have to do a little manipulation for the thing. 2, 3. Okay, this is step 2. So what we're going to do is we're going to take our output of this program, and it might be even easier to read here, so I had to make the notes for myself. So we have to divide by C. Now remember, when reading this, K is the same as M. So we have to divide by C to the Mn. And then what you do, if I wanted to form the expected value, so I basically take this is a probability generating function, and then you're going to differentiate with respect to S and let S be 1, and that's going to give us the expected value. So here it is, and here are our coefficients. So the expected value, if you had, this is for, remember, this is the number 2 by M. If I had one row, I'd expect 1 over C, 4 over C, 7 over C. I'm going to have 4 rows down in each row of size 2.